Hello and welcome to our video on absolute extrema. And I'm a little under the weather today, but we're just going to roll with it. Got to get this video out. So we're going to look at a graph, not of the normal function f, but rather the graph of the derivative. The graph below is the graph of some function y equals f prime of x, not f of x. Then the question is find all relative extrema, so local maximum, local minimums, of f of x. And we're just going to look for the locations. All we know is the graph of the derivative. So here's the graph. Let's go out 3 this way, 2 this way. I'm going to go down a couple as well. We'll plot some points. And then I'll connect them. All right, now just a little dip and back up. So again, this is the graph of f prime of x. I do not know the graph of f of x. So this is a little bit different. It makes us think, which that's a good thing. We're looking for the local maximums and local minimums of f of x. Well, it helps to know the critical numbers, right? So these are the critical numbers. So what are the critical numbers with respect to f of x? Well, that's when the derivative is 0 or undefined. Well, we have the graph of the derivative. So we have to look for where is the derivative 0? Got a few places there. So the derivative is 0 when x is -2, 0, 1, and 3. So again, it's a little different because I'm looking at the graph of f prime of x. We're looking for where we hit 0. And now I'm set up well to do the first derivative test because I have a lot of information about the first derivative. Here I've got its graph. At these critical numbers. Okay. And I know how we behave in these little intervals. I can see that the derivative is negative from the left side of -2. The derivative is positive on this interval because we're above the x-axis. So from -2 to 0, the derivative is positive. In this little portion here, we're below the x-axis, so the derivative is negative. Then we're above from 1 to 3. And then we're below the x-axis. again from 3 onward. So since I have the graph of the derivative, I can use that information to do the first derivative test. And that allows us to classify the critical points. Since the derivative is negative to positive around -2, that means f is decreasing and then increasing. Well, if you think that through, if we're going down then up, that means we have a local minimum. When x is -2. Same thing over here at around 1. And we have a local max when we're going from increasing to decreasing. We also have it at 3 here. So we can determine all this stuff just based on the graph of f prime of x. Now here's another question. So what are the open intervals where f, again, is concave up or concave down? Well, normally we would think about the second derivative, f double prime, for that. It's when is f double prime positive or negative? Well, we only really have information about f single prime, the first derivative, but that can be enough. We can use that. Remember, f double prime is the derivative of f prime. So that means where f double prime is positive, that means f prime is increasing. And likewise, if f double prime is negative, which means we're concave down, that means f prime is decreasing. So that's how the second derivative relates to the first derivative. And so this is what we use to solve the problem. My graph, or excuse me, my function f is concave up when f prime is increasing. And it's concave down when f prime is decreasing. Yeah, this goes both ways here. It's our equivalent. So the problem basically boils down to I look at my graph of f prime, look at where is it increasing and where is it decreasing. Well, we're going up along here until we hit -1. Right, then we're going down until we hit this point, which I will tell you is 1/2 minus 1/2. This point right here. And then we're increasing until we hit x equals 2. So from -infinity to -1, we're increasing. And from 1/2 to 2. So that's when f is concave up. Because the second derivative is positive. So from -infinity to 1, and then 1/2 to 2. And f is concave down when the second derivative is negative, or rather the first derivative is decreasing. So we're decreasing here on this graph from -1 to 1/2, and then from 2 onward. So there we have it. And while we're at it, I didn't ask for this, but let's talk about inflection points real quick. Inflection points of f, that's when the concavity changes. So that would be at all these numbers we see. That's where we're doing that switching around. Right, we changed from concave up to concave down here. And at all these little points. Notice that it's happening at the relative extrema for this graph, f prime. All these high points and low points. That's kind of interesting. Again, it's where the concavity is changing. So I think that's a very good problem. Tends to be a pretty standard test question. Just operating from the graph of f prime of x. So if you do happen to be taking a test, just be careful. And if you're given a graph, make sure you read it carefully, whether it's the graph of f or the graph of f prime of x. All right, now on to the main topic of absolute extrema. Another word for this is global extrema. So absolute or global extrema are extrema on the entire domain. When we were talking about relative extrema, like local maximums, local minimums, well, I use that word local, it's talking about its little neighborhood. But an absolute maximum or a global maximum is, well, global. It's over the whole domain. It's a high point. In particular, an absolute max at x equals c, we have that if f of x is less than or equal to f of c, so this is like a higher y value, for all x in the domain of f. And similarly, for an absolute or global minimum, we have one of those at x equals c if every f of x is greater than or equal to f of c for all x in the domain of f. So this absolute, that's much stronger than local or relative maximum. It's a maximum over everything. For example, let's compare the two things of absolute versus relative. It's a graph that kind of snakes around. Okay, notice I've got firm endpoints here, so the graph just stops. So first, let's look for local maximums and minimums. That's relative extrema. Well, that means that it's an extreme value within its little neighborhood. Like this up here. This right here is a local maximum. It's got a little neighborhood here where it's the big dog. It's the high point. And right here. Let's use a different color. So I'm going to point out those as local max. And local minimums. Well, that's these little valleys here. They're low points within their little neighborhood. Notice that's also true at these points. The domain is suddenly cut off, but out of everything in the domain, they're a little low point in their little nearby neighborhood. Now, an absolute maximum is not just talking about its little neighborhood, but the highest point overall in the whole domain. And that would be what I just circled. It's the only point that reaches this high. So this is an absolute maximum. Notice it's both an absolute maximum and a local maximum. Well, this is because absolute are always local when you think about it. If it's the highest point in the entire domain, then that means it'll also be the highest point within its little neighborhood. So an absolute maximum is always a local maximum too. And well, these look a little close, but this is the lower one. That's an absolute minimum. The lowest point within the whole domain. And it's also both a local minimum and an absolute minimum. Because if you're the lowest point in the entire domain, then that means you're also the lowest point within your little neighborhood. Okay, I want to show another drawing here, and I'll get a little more specific with the values. Let's go up 3. Let's go over 4 to the right. And down 2. And let's just go over 1 to the left. So I'm actually going to draw a hole at this point at -1, -2. Filled in point here at 1, 3. And then at height 2, I've got both of these, same height. And then let's go halfway up. Connect these. And we're going to draw a straight line between these two. And then just slightly go up here. So let's examine local maximums and local minimums. Use my colors again. So local max, that's a maximum within its little neighborhood. Well, that would be this one. And you can take a little neighborhood here. And it's the big point. Notice that this one actually works as well. You can see it, at least in my definition of absolute extrema, and it's like this with relative as well. I'm just not going to go back to it. We use these inclusive inequalities where you allow for equals. So I can make a little neighborhood here using an open interval with the x values. And this, oh, that's actually a low point, isn't it? Yeah, that's what I meant to say. Let's talk about that. This is true for both of them, actually. Where they're a low point within their little neighborhood, and that includes points of equal height. By that definition, that's also technically true of every point in between, if everything is equal height. But that's not very interesting to talk about, so I just ignore it. This is supposed to be flat, by the way. And here's the other local maximum. Since it's an endpoint, we're only concerned about this side. And it is a high point within that little neighborhood. Now let's talk about absolute. So this is the absolute high point out of everywhere. So we have an absolute maximum of 3, that's the y value, at x equals 1. Now, is there an absolute minimum? Well, it kind of looks like this could be, but notice I drew a hole there. It's missing. So there actually is no absolute minimum here, because we'll pick any y value in the range of this graph, and you can always get a little bit lower. For example, if I look at a point here, like let's say that's negative 1.9, I could always get a little closer to that hole by negative 1.99. I can get a little closer than that, negative 1.999, and so on. You can always creep closer and closer to the y value of negative 2, but you never quite reach it. So it's like an asymptote in that sense. So there is no strict absolute minimum value that this graph reaches. So it just asymptotically approaches negative 2. So no absolute minimum, because of the hole. The minimum wants to be where that hole is. And we can always find a y value that's a little bit closer to negative 2. So this leads to the extreme value theorem. What it does is it lays out certain cases where you're guaranteed to have both an absolute maximum and an absolute minimum. Or really, it's one case, but 2 conditions. That's what I mean. If f is continuous, so that's one condition we need. And it's continuous on a closed interval. Now, technically, the real extreme value theorem is a little bit stronger than this, but we'll just stick with this formulation of it. So if f is continuous on a closed interval, then it's guaranteed that you have an absolute maximum and absolute minimum. Which can be good to know, as we'll see. On that interval in particular, on that closed interval. I want to show you just a little bit why this is true, why we need these conditions, rather. So why do I say that it has to be on a closed interval? Let's start there. We've actually already seen this in the previous example. So let's look up. This was not defined on a closed interval because I was missing this endpoint. So that would be an open interval on this side at least. And because of that, I had this situation where I did not have an absolute minimum because I just removed it. So that's why one of the reasons why we need a closed interval. You can have that sort of thing happen. Now, why do we say that it must be continuous? Continuous on a closed interval in order to guarantee an absolute maximum and absolute minimum. Well, we're going to look at a case where we are defined on a closed interval, but we're not continuous, and it's going to fail. Not being too particular about my points here, but could have something like this. We're defined on a closed interval, right? These are all supposed to line up, by the way, same x value. So we're defined on that entire interval because I've got this point right here filled in where we were missing. But I actually have neither an absolute maximum nor an absolute minimum because they want to be here. That absolute maximum is missing. Or I should say no absolute minimum is missing. Even though we're defined on that entire closed interval, but because we're not continuous, because I have this little jump right here, I could have this weird situation where I have holes where the absolute extrema want to be. So these give you an idea of why we want both. We want to be continuous and be that way on a closed interval. Then that will guarantee that you have an absolute maximum and an absolute minimum by the extreme value theorem. Well, now the question is, how do we find them? And I'm talking about if we don't have an obvious graph, how do we find these absolute extrema just based on the function alone? Well, we've already spent the past couple of sessions talking about how to find local maximums and minimums using either the first derivative test or the second derivative test. And now I'm going to discuss the process of finding absolute. Well, so first off, you need the conditions for extreme value theorem to hold because we want to use that theorem. So we want f to be continuous on a closed interval because that guarantees that these things exist in the first place, and we need that. And this is a result of extreme value theorem. So to solve this little puzzle, I want a guarantee that these things even exist in the first place. And then we make use of the insight that every absolute maximum and minimum is already a local maximum and minimum by definition. So what this tells us is in these certain conditions, I know that these things exist, and then the candidates come from the pool of local maximums and minimums. So that's the idea. How do I want to say this? Let's see. Every absolute maximum and minimum is a local maximum and minimum by definition. So they are our candidates for absolute. The local are, that is. So I find the local extrema, or relative extrema, and then I'm just going to compare which one gives me the highest and lowest values. We know that the absolute max and min exist. So, and we know that it's going to be from this list here. So that'll tell us. Essentially, the local maximums and minimums, they narrow down our search. We know that they're there, and then finding the local extrema narrows our search. Okay, so I want to say it this way. So we find the critical points because they serve as candidates for the local maximums and minimums as well. So find the critical points, and then the highest and lowest values must give the absolute maximum and minimum respectively. Okay, by extreme value theorem, I know that these things are out there, and I know that they must come from the list of the local maximums and minimums, which happen at critical points. So I find the critical points and then just compare all the values, and that'll do it for us. We will find the absolute extrema. Excuse me, I want to say 3x to the 4 plus 4x cubed minus 36x squared plus 30. And this is on the domain -4 to 4. Again, I need this. I need to be continuous. That's what polynomials are always continuous. They're a great example of that. And on a closed interval, I need this because by extreme value theorem, that guarantees that these things exist in the first place. Otherwise, we could be looking for candidates, but I wouldn't necessarily know that all of those candidates are absolute extrema. I need to guarantee their existence first. So that's why I'm harping away at this. It's actually important. Well, we will need the derivative because we need to find critical points. Those are our candidates. Okay, it helps to factor as much as we can. We can factor out a 12x. Gives me x squared plus x minus 6. And that factors further the plus 3 and minus 2. So this will always be defined, so I don't have to worry about that whole undefined bit when searching for critical points. Let's set this equal to 0. And since it's already factored, this is pretty quick. Well, the critical numbers, that's just the x values of the critical points, are at 0, -3, and 2. That's when the derivative is 0. Well, are there any other critical numbers? So we've covered right here, these are when the derivative is 0. This derivative will always be defined. It's a polynomial. Well, remember there was another kind. Whenever you have endpoints in your domain. With these closed intervals, my domain is suddenly cut off at -4 and 4. So we have to check those points because they could be absolute extrema. So we have to check all these critical numbers. And we're not going to do the first derivative test nor the second derivative test. We don't need to. Those will help you find local extrema. But for absolute, I just need to plug these numbers in and compare the y values. That's it. I like to write them in ascending order. So I'll spare you the time of calculating all these things. Just tell you the results when you plug these into the function f. These are what I got. So you have to take a little time to plug those numbers into f. And then you just search for the biggest number, like this. And the smallest number out of these. So this is an absolute minimum of -159 at x equals -3. And we have an absolute maximum of 478 at x equals 4. So notice it was really important that we checked the endpoints because we really did have our absolute maximum there. So just a little visual real quick of why we needed this. Well, so the type of critical point where the derivative is 0, that's where it looks like a hilltop or a valley where the graph becomes flat because you have a horizontal tangent line. So the slope of the tangent line is 0. So this is the type where the derivative is 0. Where you have this smooth hilltop or a smooth valley. You could also have a local max or min when the derivative is undefined, like at a corner or a cusp, where you have this sudden change in slope. But it could also happen at an endpoint because you could have something like this. Say my domain is suddenly cut off. Well, in a place like this, the derivative's not 0 because we're not flat, and it's also not a corner or cusp. The derivative is defined here on our domain because our domain is only involving one side. So that's all we even have to consider. So there's no disagreement coming in from the other side because there is no other side. So that's just a little visual of why we need to check endpoints. We had to do it here in this example we just did. Okay, let's do another example where we find the absolute extrema for f of x equals e to the x over x squared plus 1 on the interval from -2 to 2, and it's a closed interval. Well, are we continuous on this closed interval? And the answer is yes, because notice this will never be 0, this denominator here. No matter what I plug in, since this x is squared, it's always going to be either positive or 0, and then I'm adding 1 to it. So the denominator can never be 0. And e to the x is also perfectly fine. It's always continuous. So this is something you want to check. You want to guarantee the existence of these things first. So note f is continuous. On the interval. And we can know this for certain since this is a polynomial. The denominator is, I mean. And it's never 0. And so it's perfectly well behaved, and so is the numerator. So this means we can use extreme value theorem. By extreme value theorem, we know both the absolute max and min exist. They both must exist. And this means that when I look at all the critical points, I know that these things must be in there. So that means I just look at all the critical points and compare them to each other. Find the biggest one and the smallest one, and we know for certain that those must be the absolute maximum and the absolute minimum. Because they exist, and they must be local maximums and minimums too. So we find our critical numbers by taking the derivative. We've got a little quotient rule here. That's a quotient. So big fraction, low, d high. Well, derivative of the numerator is still just e to the x. Minus high, d low, 2x is the derivative of x squared plus 1. All over low squared. That's quotient rule. And now it's helpful if we can simplify. Notice they have an e to the x term, or factor in both terms, I should say. So I can factor it out. So I've got the x squared plus 1 plus 2x left over x squared plus 1 squared. And now it might help us if I just rewrite that polynomial in the more standard order, writing the 2x first. It's a little easier to see how that factors. It does indeed factor nicely. Oh, I made a mistake. You see it? This was supposed to be minus 2x. Sorry about that. Caught it. There, this is how it factors. I knew it had to be this, so I was confused why it was a plus 2x. Yeah, it should be minus 2x. So that's convenient, just factoring that. Now, let's think about critical points, or critical numbers. Are there endpoints? And the answer is yes, because I've said we're on this interval from -2 to 2. So -2 and 2 are critical numbers. We have to check them because they could be local maximums and minimums, and hence could be absolute. Well, is the derivative ever undefined? Well, it might almost look like it because we are dividing by stuff, but again, this will never be 0. And e to the x is also perfectly well behaved. I can plug in any x to that. So that's not an issue here. This is always defined. But could this ever be 0? And the answer is yes. Well, whenever you have a quotient equal to 0, really all that matters is the numerator. Because it could help to think of it this way. I could multiply both sides by this denominator, and I would still have 0 over here. So the numerator is the only thing that matters to get us equal to 0. Helpful fact about e to the x, which you want to know, is that it's always positive. So always above 0. So that's not going to get us 0. It's going to come from these. And it's actually the same x value there, so x equals 1. So the critical numbers, when x is 1, that makes both of these factors 0. The e is not going to get us 0 ever. And remember, we have endpoints here in this problem. So these are the only critical numbers. Now I know that the absolute max and min exist by extreme value theorem, and I know that they must be among this list here. So I just plug all those x values in and compare the heights. And so this was e to the -2 over 5. So it was e to the 1 over 2 when you plug into f of x. This is e squared over 5. But we'll need our calculator for this to get a sense of which number's bigger, which number's smaller. Well, this top one will definitely be the smallest one because of that negative exponent. But I'll go ahead and tell you the number. It's what I got. About 0.027. When you plug in 1, I got roughly 1.36. And I got roughly 1.48 when I plugged in 2 for x. So since this is the smallest one, and I know the absolute minimum must be one of these things, then it's this one, the smallest one. And again, I know the absolute maximum is somewhere out there, and I know it's somewhere among this list. So then it has to be the largest one on this list.